Aluminum oxide ceramic and effector, the component that physically picks up and places silicon wafers inside semiconductor process tools. The paddle type is a single flat blade that slides under the wafer and supports it across its full area. The fork type uses two parallel prongs that contact only the wafer edge zone. Both share the same mounting interface, a triangular head with bolt holes that attaches directly to the transfer robot hub. And both are machined from high-purity alumina ceramic, because the material that touches a wafer inside a fab determines whether that wafer comes out clean or contaminated. Flexural strength above 350 megapascals, enough rigidity to hold a 300 mm wafer flat without deflection, even at full extension from the robot hub. Ultra-low particle shedding. The dense sintered alumina surface releases negligible particles during wafer contact, keeping defect counts within process specification. Flatness controlled to better than 0.05 mm across the full blade length, so the wafer sits level and the vacuum chuck receives it without alignment error. Thermal stability up to 1400 degrees Celsius, allowing the arm to retrieve hot wafers directly from deposition or anneal chambers without warping. And dielectric strength above 10 kV per millimeter, providing complete electrical insulation that prevents static charge transfer to the wafer surface during handling. Two configurations serve two handling strategies. The paddle type supports the wafer across its full area, ideal when the wafer is hot or when the process requires uniform backside contact. The fork type contacts only the wafer edge zone, required when the wafer backside carries active layers or coatings that must not be touched. Both types are machined with custom arm length, width, thickness, bolt pattern, and tip geometry based on your transfer robot specification. ADCERAX produces both from the same high-purity alumina, with the same flatness, surface finish, and particle performance standards. A transfer robot reaches into a AD₂O₃ cassette, slides its ceramic and effector under a 300 mm silicon wafer, lifts it out, rotates, and places it onto the electrostatic chuck inside a process chamber. That sequence happens thousands of times per day, and every single time, the end effector surface is in direct physical contact with the wafer. If that surface sheds even a handful of particles, those particles land on the wafer backside, transfer to the chuck, and eventually cause pattern defects on the front side, defects that kill dies and reduce yield. A metal end effector would corrode, generate metal particles, and create galvanic charge on the wafer surface. A polymer arm would deflect under the wafer weight, drift with temperature, and outgas organics into the vacuum chamber. Alumina does none of these. The dense sintered surface releases negligible particles, keeping the wafer backside as clean as the moment it entered the fab. The 350 megapascal flexural strength holds the wafer perfectly flat, even when the arm is fully extended and cantilevered from the robot hub. The thermal stability means the arm retrieves a wafer straight from a 400 degrees Celsius anneal step without warping or dimensional drift. And the dielectric insulation prevents any static charge buildup that could damage gate oxides or attract particles electrostatically. From atmospheric EFEM robots to vacuum transfer modules, from 200 mm legacy tools to the latest 300 mm platforms, alumina ceramic end effectors are the standard handling surface that separates a clean wafer from a contaminated one.